Hello everyone, and let's start with our code. Here you can see libraries and reproducibility part, and here's part 1. The first thing here we are doing here is loading the minist dataset. You can see here, and that's just a standard dataset of handwritten digits 0 to 9. It comes built in with keras, so we don't need to download anything extra. You know that. And right after loading the data, we normalize the pixel values. These images originally come with pixel values ranging from 0 to 255. And what do we here is convert them to float 32 and divide by 255. Sorry, 55. Okay, so everything falls between 0 and 1. It is a small thing, but it helps the model train more efficiently. And that's okay. Then we expand the dimensions of the input. By default, the images are 28 by 28 grayscale images, meaning they don't have a channel dimension. But most convolution layers in Keras expect a 3-dimensional input with a channel, even if it is just one. So we add that extra dimension at the end using expand dims. You can see. And after that we converted labels to one hot format. You can see. Basically, instead of having just a digit like 5, we turn it into a 10-dimensional vector where only the 6th element is 1 and the rest are 0. And this makes it compatible with the softmax output layer we will use in the model. Now, speaking of the model, let's look at how it's built. You can see here simple CNN model. And we are using sequential model here, which is the simplest type in Keras, and we are stacking layers one after another. We start with a Com2D layer with 32 filters and 3 by 3 kernel using ReLU activation. It also takes the input shape, which is 28 by 28 pixels with one channel. At max pooling, here we downsample using max pooling. Then there is another convolution layer, this time with 64 filters, followed again by max pooling. And we flatten the output after that. Flatten just takes that multidimensional output from the com layers and reshapes it into a single vector, so it can go into a dense layer. Then comes a dense layer with 128 neurons and ReLU activation. A dropout layer is added right after to prevent overfitting, and 30% of the neurons will be randomly ignored during training. Here you can see 0.3. And finally, we finish with a dense layer with 10 units, one for each digit, and we apply softmax to get a probability distribution over 10 classes. That's the basic CNN model we will be using across all clients. And okay, now the next step is simulating what happens in a federated learning setup. In a realistic federated scenario, each client doesn't see the full data distribution. Some clients might only get a few classes or a biased portion of the data. And that's what we are doing here in this function called create non-IID clients. So what does it actually do? First, we select the label for each sample by taking the argmax across the one hot encoded labels. That just gives us back the digit as an integer. Then we build a list of indices for each class. Basically, we are organizing the data by digit. And now comes the main loop where we simulate each client. And for each client, we randomly pick a few classes. By default, it is 3, and we sample data points only from those classes. So a given client might only see digits like 1, 5 and 7. That's the non-IID setup. And within each selected class, we randomly pick some samples. The total number of, number of samples is uh, 600 divided by the number of selected classes, just to keep it balanced. And after collecting those samples, we shuffle the indices and assign the selected data to that client. Each client ends up with their own subset of inputs and labels. And I hope that part is okay. So here the training part. This is where each client trains locally using the Fedprox method. And let's take a look at the local train Fedprox function. The goal here is to train the client's model using its own data, but also make sure it doesn't drift too far away from the global model. That's what the proximal term is for. We will get to that in a second. We start by setting the client model's weights to the current global weights. That way each client starts training from the same point. Then we define an Adam optimizer and prepare the dataset. It's shuffled and batched like you would expect in any standard training loop, right? It's okay, I think. And inside the main training loop, we go through each epoch and each batch. We use TensorFlow's gradient tape to track the operations. We make predictions, calculate the cross entropy loss. This is just the usual classification loss comparing predicted labels to actual labels. And then we take the average loss across the batch. And here's the important part, the proximal term. And what is that proximal term? What we are doing here is calculating how far the client's current weights have moved from the original global weights. We loop through all trainable weights of the client model and compare them to the corresponding global weights. For each pair, we compute the square difference and sum them all up. That gives us a single value, the distance. Then we add this distance term to the regular loss, but we scale it using the mu parameter. You can see mu, and that parameter controls how much we want to penalize clients for drifting too far. If mu is 0, we are basically doing fat average, and if mu is larger, clients are more tightly pulled toward the global model. And I hope that's okay. Once we have the total loss, the combination of base loss and proximal term, we compute the gradients and update the client's model like usual. And at the end, we return the updated weights. These are going to be sent back to the server. That's okay, I hope. And let's switch. Here the fat AVG function is doing exactly what the name says. It takes all the clients' weights and averages them layer by layer. So if 8 clients participated in the round, we take the mean of their corresponding layers and use that to update the global model. And it is worth mentioning, this averaging is what gives fat AVG its name. And Fedprox still uses the same update step. The only thing different is how local training is done. And okay, now in the federated training loop, this function here, we run everything over multiple communication rounds. At the beginning of each round, we randomly select a percentage of clients. In this case, 80% of them will participate per round. That's okay, and for each selected client, we build a fresh model same architecture as the global model and train it locally using that local train Fedprox function we just went through. And after that, we evaluate the new global model on a small part of the test set. Here we are just using the first 1000 samples from the test data. This gives us an idea of how the model is doing as training progresses. And the validation accuracy is stored in a list and we print it after every round just to track progress. And finally, when all rounds are done, we return that list of accuracies so we can pull out or analyze it later. And I hope that's okay and we can look this part, here around Fedprox training. Let's look. Here we start by generating the client datasets and we are taking the first what is that 20,000 samples from training set and splitting that across 10 clients. Each client will get a non-IID set, non-IID subset like we set up earlier, right? Then we build the global model, same CNN as before, and compile it. We are using categorical cross entropy for the loss since this is a multi-class classification problem and we are tracking accuracy as the metric. Now comes the training loop. We call the federated training Fedprox function and pass in the global model and the client data. We are running for 20 rounds and using 80% of the clients each round, and each client does 2 local epochs with a mu value of 0.01. That's okay, I hope. And this whole process simulates what happens in a real federated learning scenario. Clients train locally, send back updates, and the server updates the global model by averaging. Now, after training, we want to take a look at how well the model did over time. So we plot the validation accuracy from each round. The x-axis here is just the number of global rounds and the y-axis is accuracy on validation subset we used after every round. And this gives us a quick visual to see how the model improved over time or if it plateaued. And finally, after all the runs are done, we evaluate the global model one more time, this time on the test, full test set. And here are outputs. Let's look at this, what's happening here. Here, each row shows the set of clients that participated in a particular round and validation accuracy we got after aggregating their updates. You will notice that in every round the client set is different. That's because we are randomly selecting 80% of the clients each time. And this randomness adds some variation which is expected in federated learning. And at the start in round 1, here we can see the validation accuracy is pretty low, around 0.2. But that makes sense since the model is just starting out and hasn't learned much yet. And let's look, by round 5 we have already up around 0.6. Then from there the model keeps improving steadily. Let me show you. And there is a little bit of fluctuations here and there, like round 9 dips a bit compared to round 8, but overall the trend is going up. This is what we want to see. The model is learning and generalizing better as more client updates come in. And by the time we reach around 20, we are at 0.835 on the validation set, which is pretty solid. So even with only partial client participation and non-IID data, the model is still able to learn a decent global representation. And visual part here. This is a simple plot of validation accuracy across the 20 global rounds. It gives a clear picture of what we just saw in the logs. So the horizontal axis here is the round number and the vertical axis is the accuracy. What you can see is that the first round show the steepest gain. The model goes from around 20% to about 60% pretty quickly. Then the curve starts to level off a bit, but it still keeps going in general. There are a few small dips here and there, which again is normal due to the random nature of client selection. And toward the end, the model accuracy is consistently staying above 80%, which is where we want to be. And finally, after all the training rounds, we evaluate the model one more time, this time on the full test set. The final test accuracy comes out to around 87.3%, which is quite good given the setup. We used only 20,000 training samples split across clients in a non-IID way and still ended up with a solid performing CNN. So yes, this gives us a working Fedprox implementation running on realistic federated conditions, and the results show that the method is holding up well.